everyone, I'm going to introduce to you the machine learning confidence intervals for COVID-19 forecast method that I developed with Isabelle Guillon. Since COVID-19 was declared a global pandemic, governments' policymaking have been driven by COVID-19 forecasts. Now, despite the numerous literature on the subject, there is no real consensus today on the forecasting methodology, and this may have led to ill-suited policies implemented, causing human and economical loss. Looking closer at current COVID-19 forecasting models, one of the main approach is to use compartmental epidemiological models, especially the simple SIR detailed in this ordinary differential equation system here. Basically, in this model, you divide the population in 3 compartments. You have the S compartment, where people are susceptible to get infected, the I compartment in red, where people are infected by the disease, and the R compartment, where people can be either recovered or have died from the disease. To go from one compartment to the other, you have the transmission rate beta and the recovery rate gamma, and you need to estimate both parameters to solve this system here and eventually obtain each compartment evolution in time, as illustrated in this figure, where we have the number of people in each compartment on the y-axis. We're actually interested in the red curve here, the number of infections. But these are daily infections, which can be very noisy in reality, so we focused on cumulative infections, which is basically the sum of the red and the green curve. Another approach is to use deep learning models, but they can be hard to interpret, so we did not pursue in that direction. One big limitation that we found is that only a few papers detail their interval forecasting models. Now, interval forecasts are more reliable than point forecasts, and we only found methods based on Bayesian approaches that are quite computationally expensive, or naive methods that are not always reliable. This is why our primary objective was to develop an alternative interval forecasting model. With our method, it is possible to map governmental measures and forecast cumulative cases 15 days ahead and predict each prediction horizon error bar, as illustrated here, where we have the black dots as the true observed cases, the blue crosses is the forecasted cases, to which we assign a predicted error bar with the darker blue shaded area, and the lighter blue shaded area is the actual error bar that we want to predict. Now, for this study, we focused on 54 countries. We used cumulative COVID-19 cases, and we used country stringency indexes, which are basically the sums of non-pharmaceutical interventions in the country, like lockdown, testing policies, mask policies. And this stringency index will help us take into account governmental measures in the model. Now, for the underlying forecasting model, we used an SIR compartmental model trained on each country. Now, in our framework, the transmission rate beta is actually a linear transformation of governmental interventions in the country, so this stringency index that I talked about. We train the model on each country. We estimate the stringency parameter W and the bias, and eventually the model will return cumulative cases 15 days ahead. Now, for the second part, the machine learning confidence intervals, we didn't have enough real country data, so we generated synthetic data, COVID-19 data, and the target that we want to predict here is the absolute difference between our simulated data and the predicted cases. So this error sigma here. To predict that, we trained one random forest regressor at each prediction horizon, so we have 15 of them. We use this past data as training inputs, and each random forest regressor basically returns the predicted error bar, the corresponding horizon, as illustrated here with the light blue shaded area at each horizon. To assess our intervals reliability, we used the negative log likelihood that we want to minimize, and we compared our method to a naive and bootstrap method. The idea was to train the model on simulated data and test it on real country data. So here are the results on real country data. We can clearly see that our method outperforms, our method in blue here outperforms the state of the art. It minimizes the negative log likelihood at every prediction horizon. Looking closer at the intervals we predicted, we can see that the black dots, so the observed COVID cases are always contained at 1 or 2 sigmas intervals, which is what we want to achieve. Now, as a conclusion, we developed a reliable alternative method that is less computationally expensive. It only takes a few hours to train all the random forest regressors, and it appears our method is robust to countries' heterogeneity. Obviously, the method also requires some future work. Thank you for your attention.